Welcome back to another tutorial. Today we are going to recreate Fhen by Zombie. This is a puzzle game where you have a bunch of numbered blocks placed along a level. By selecting one, you get to see all the possible moves that box can make, with a digit denoting the number of spaces it can travel. Swiping moves the block to the specified direction. If the box detects an obstacle within its path, it would jump over before resuming its counting of spaces. To win the game, you have to reach the goal. The idea itself is rather simple, so with this tutorial, I will explain the process of decomposing its mechanics, and hopefully by the end of this video, we would have made a recreation of the game. Anyways, let's get started with the tutorial. First things first, let's talk about our assets. We have a black box for which we'll place copies of around the level. We have the gold block with a checkered pattern on top. We also have an identical black box. Keep in mind that these are two different blocks with different purposes. This one will be used for initializing the boxes within the level, while this one will be our reference when we spawn blocks later down the road. Finally, we have our decorational blocks. Notice how they are only 2 voxels high. That info will be important later. All of these blocks are unglued from all sides so that they don't connect to one another. They also have box colliders while the Decor have none. Let's kick things off by opening the gold block and assigning it to a variable. Make sure that it is set to global so that we can access it anywhere within the level. For the box, let's create a global list and save the block there. Then, let's set the number of spaces to 1 before making another copy to modify it via this input wire. Make sure to go 1 voxel up and 3 voxels left on the bottom right corner to easily attach to its input. Then, we'll use that value to save it to a list to keep track of each block's number of spaces. The reason why we have 2 instances of this variable is so that in case this input wire isn't connected to anything, it would still have a default value of 1. And the reason why we chose 1 is because if it was 0 instead, the block would practically have no use as it wouldn't move anywhere. Then, increment the list length. Next, let's bring out a script block to store our main code. We'll begin by setting up the camera. Bring in the variables for the position and distance, get the world size, add the 2 vectors and scale it by 0.5 to get the center of the level. Get the distance between the 2 points and multiply it by 5 to get our zoom. For the rotation, set it to 75 in the x-axis. Do the same for the light rotation, but set the y value to -135 to have some angled shadows. Finally, let's plug in our cam variables. Since there aren't any blocks, we get a close-up of the origin point, which is where the script block is. If we place some blocks here, the camera now situates in the middle and it zoom in closes the 2 blocks to our screen. Afterwards, we now have to create the digits to display on top of our boxes. To save some space with the custom blocks, we can actually stack them on top of one another as long as they are all unglued. So, let's go ahead and create our numbers from 1 to 8. Now, we essentially have 8 blocks within this cubic space. Make sure to set its type to physics to easily position them later. Let's initialize the numbers. At the start of the game, we'll be saving these blocks into a list. One trick you can do when storing a lot of items in a list is to attach a list element to another list element with an index of 1. This is because those indices add up. That way, we can actually specify the first, second, third, fourth item, etc. Then comes the very tedious process of connecting each wire to a specific digit. This will take a while, so be very careful and make sure that each layer corresponds to a pink arrow. After all that, let's loop through our boxes. Create a copy of the digit based on the block's number of spaces, get the index, and save it to a list. Make sure to lock its position and rotation as it's a physical block and we want it to be static. Then, create another loop for our boxes. Here we'll set the visibility of the numbers based on a new boolean property that checks if the box has been moved, because by that point, we don't want to display the digit anymore. Then, we set its position to appear on top of the box. Let's replace these bricks with our black boxes, and when we press play, we can see our blocks with numbers on top. And if we modify this value, that also updates the digit. Let's also quickly move our gold block to the bottom. Break the vector, keep the X position, set the Y position to negative 0.45, and move the Z position ever so slightly by 0.001. Now we can only see the top layer of the wind block. Also, the reason why we gave a slight offset to the Z value is to avoid any form of Z fighting. This is a phenomenon in rendering that occurs when there are two or more objects sharing the same coordinates. When this happens, their surfaces overlap and the game cannot determine which object to display first, resulting in a flickering effect. The next thing we have to do is to implement the controls. First, bring in the truth variable stop and add a not block to invert the state and save it to a variable. We'll use this boolean to enable our controls. Place a touch sensor set to begins. On touch, get the position by converting the screen coordinates to world positions and use a line v plane block to find that point within the level floor. Next, we'll have to loop through the list of boxes to find the closest match. We'll need the ID of the nearest block and its distance from the touch position. Set BID to -1 and best to 1. Then, loop through BSLN. Let's get the distance between the box's position and the touch position and check if it's less than the best variable. We'll also check if the box hasn't been moved yet, as we don't want to look for boxes that have already traveled. If this is true, then we update the variables. At the end of the loop, check if BID still has the same value. If it's greater than -1, that means it found a match. If that's the case, let's introduce a new variable, selected, which is the ID of the current block. We'll check if our ID is equal to this variable. If it is, then we would actually want to deselect, so set it to -1. Otherwise, update the variable with our found ID. While we're here, let's also initialize its value to -1 so that nothing is selected. If we do have something, however, then we will need to create the markers which will position along the selected block's cardinal directions. The number of marks in each line depends on the specified number of spaces for that box. Create a loop where the stop index is set to the block spacing multiplied by 4 to cover all directions. Clone the marker and save it to a list. Set its rotation to 45 in the y-axis before updating the list length. Let's also add in a button as effects to indicate that we have picked the box. If we inspect the value of MSLN, notice how it is increasing every time we select a block. To avoid this, we will need to reset the list by deleting all of the markers and setting the length back to 0. And that did the job. We have set up a system in a way where a list of markers can be treated as a table with rows and columns. Each row represents a direction to travel to, and the number of columns are based on the current block's number of spaces. This is what we call a 2D list. It is essentially a list consisting of smaller lists. In this next bit, we'll be using two loops, one for determining the row and one for the column. Combining these two will allow us to get each cell within the table. For the first loop, have it run 4 times to encompass all 4 directions and save the index to I. Let's also introduce the variable off, which acts as the offset for positioning where the markers would be. We want to reset its value before we proceed to the second loop. Here, set the number of iterations based on a list length divided by 4, which is the number of markers per line, and save the index to I1. Next, we'll find the actual index by combining these two variables. Take the second loop size and multiply it by I to specify the direction before adding that value with I1 to specify the order in that row. Add an if condition, which is set to true for now, then set the marker's visibility based on whether the controls are active. Next, let's discuss the idea on how we'll position the markers. We'll use the box as a starting point and add an offset from that. The offset will be a vector with a magnitude based on the sum of our off variable and the index from the second loop, which will then be rotated based on the value of the first loop's index multiplied by 90. Let's say this box can travel 4 spaces along any direction. While the first loop is in its first index, the direction will be facing forward. It will also run a second loop and go to each point towards that direction. Seeing as there weren't any obstructions in its path, the loop now proceeds to the second index, which sets the direction to the right. At the second loop's second iteration, it detects a block that blocks the block from going across. This is where our off variable comes in. We keep increasing its value until we find a position that isn't occupied by anything. It then places the marker here and resumes with a loop. Once the loop is over, we reset the variable back to 0. This process is then repeated until we have markers in all 4 directions. Now that we know what to do, let's start placing the scripts. To check for blocks, we'll be using a raycast. A raycast is essentially a line that goes from point A to point B, or in this case, the from and to inputs. It traces a line between these 2 points and checks if it hits an object before returning as a boolean. If it finds anything, it outputs the point of intersection and the object it hit. The call of the line is an indicator on whether the raycast has hit anything or not, with red being true and green if not. The raycast can only detect blocks with colliders, meaning it has no effect on pass-through blocks and script blocks. We'll be using the vector and adding an offset of 2 in the y-axis to use it as a starting position, before decreasing its y position and using it as an end position, making this go from top to bottom. If it hits anything, then we increment the off variable and loop back. Otherwise, we set the marker's position to go there. Let's quickly see if this works, and it's all going well. The number of markers in each direction is based on the digit on top of the chosen block. If we bring this box to obstruct the path of the other block, you can see that it jumps over before continuing. Let's also update the marker's rotation by using a loop block to smoothly turn that block into place. Don't forget to annotate your code with comments to keep it all organized. Next, it's time to update our controls to slide our chosen block towards a direction. We'll start with an if condition that checks if the selected variable has a value other than -1 and if the block hasn't already been moved. For this next bit of code, we'll be using a swipe sensor. This block executes whenever the user performs a swipe gesture. It also outputs the direction of the swipe. One thing to keep in mind about this block is that the direction will always give a cardinal direction. In our case, since the camera rotation isn't altered in the y-axis, we can just swipe as usual and we get our expected results. But, say it was rotated by 45 degrees, you would need to swipe in a diagonal to match a vector direction. Let's connect this to the false output so that this can only run if both of these conditions are false. Save the direction to a variable and update the block's property to true. Now, we face another problem. We need to convert this vector variable to a number from 0 to 3 to determine which row of markers we'll use as reference when we spawn the blocks. Maybe we can use the look rotation block. As the name suggests, this outputs rotation that points towards a specified direction. We have 2 inputs: direction, which is where you want to look in, and up, which determines which way is up, though by default this should point to the positive y-axis. Since our swipe variable is a cardinal direction, we can attach it as it is to this block. We'll also leave the second input unwired, since its default value matches with our upward direction. From here, we should get a rotation with a y value between -90 and +90. Let's break this rotation and divide it by 90. Since our vector is orthogonal, that value will almost certainly be a multiple of 90. Though let's round it in case of any decimals. We also have to use a modulo to clamp our values between 0 to 3. Let's also add a new variable that checks whether the game is currently placing blocks. If we go ahead and inspect our direction and chosen index and briefly unplug these wires, you can see how each direction corresponds to a specific number. Now that we have a new boolean, let's update our game state. We also want this to be false when activating our controls, as we don't want to do anything while the game is in the midst of placing blocks. So, invert its value and combine them with an end block. This works, although if we rearrange this so that we get the complement of this union of values, we get the same result. This is also the same principle that we use down here. The reason being, if any of these booleans are true, then the whole thing becomes true because we only need one of them to be true, which is then reversed to become false. And if any of these booleans are true, then they become false via these blocks and the whole thing becomes false as both inputs have to be true. This right here is a textbook example of the De Morgan's laws. They are a pair of rules common in propositional logic and Boolean algebra that correlates mathematical statements to their opposites. The first law, which is what we talked about, is about how the complement of a union of two sets is equal to the intersection between the complement of the first set and the complement of the second set. The second law, however, is about how the complement of an intersection between the two sets is equal to the union of the complement of the first set and the complement of the second set. You can apply this structure to set theory, probability, or in our case, developing logic gates. Let's go back to where we position the markers and have it execute when we are not placing anything. Create an if statement that runs when this boolean is true. From here, we'll be implementing a makeshift loop that runs every X amount of frames as it goes through all the markers of the chosen direction. Let's get the number of spaces and check if the new variable placed is less than that. If it is, which it would be since the value is 0 initially, then we set up a timer that goes down until it reaches 0. Once it's finished, we reset it back to 5 frames. Then, we create a copy of the clone block, aka the one with no blue wire attached to it, and save it to a list. We'll also update its position to be where the specified marker is, as well as modify the rotation a bit. We take the number of spaces and multiply it to the index of the chosen direction, before adding it with the number of placed blocks. Finally, we increase the amount and list length. Let's also top it off with some sounds. Once the number of placed blocks isn't less than the number of spaces, then we change our boolean back to false, reset our variables back to 0, and delete all the markers. If we go ahead and test this, we can now spawn lines of blocks based on where we swipe. Though let me quickly fix this SFX to be the right sound. Next, let's loop through our spawn blocks and update the rotations to go back to 0 via a loop. And we press play, we now have a cool animation as we place these clones. After that, it's time to set up the win condition. It's pretty basic, all we have to do is draw a recast on top of the go block and look for any blocks. If it detects anything, then we win. Again, we want this line to go from top to bottom to effectively hit potential objects. If this is true, then we stop the game, add a beep sound effect before finishing it with a win block. Now, we can win the game as soon as a box reaches the goal. Finally, we can now focus on adding some flair to our levels. Remember the Decor blocks from the very beginning? The idea is to scatter these around the level, making sure that they don't overlap one another. First, let's create a module that saves them to a global Decor list. Next, let's attach them to our blocks. Now we can't just leave this in the level as it would clearly mess up with our camera. So we need a script container to hold all of these blocks. In a way, this would also help us set up custom themes to our levels. By having an array of these containers filled with decorations of varying colors, we can instantly change the look of a level by placing one of these bad boys and altering the background color. So let's go ahead and do just that. Once that's done, let's head to our main code and onto the initialization stuff. We are going to have a loop wherein the number of decor around the level will depend on how big the level is. To achieve this, take a getSize block and subtract its max output by the min output. By inspecting this value, we are able to get the size of our level. Now, let's break that vector and get the larger number between our x and z values. Multiply that by the frequency and use a min block to establish a limit as we don't want to spawn too many blocks. Let's set the maximum amount to 20. Then, create a copy of our random decor by going to the list length and flooring it before saving it to a list. Let me explain how we'll scatter them around the level. We take the coordinates of our level edges and expand them a bit to cover more area. From here, we randomize the x and z position between our coordinates, snap them to the grid and pack them into a vector. Then we check if there is anything occupying that space, from black boxes to fellow decor blocks. If there is, then we look for another point. Otherwise, we place the created block there. Notice how the y position is 0.26. This is because our deco blocks are 2 voxels high, and each voxel is about 0.125 units high. We have offset it a bit to only show the top layer. Get a get size block, subtract or add to it with a vector to increase our area before breaking them. We then randomize between our given values. Make sure to floor them and add by 0.5 to snap them into the grid before connecting them to our variables. Then, we set up a raycast to check the position and save it to a truth variable. Afterwards, loop to the list of the created decors. It's important to distinguish these 2 variables, although they share the same name. Since this is a global variable, it is totally different from the other one. We then update the value of our boolean by checking if the vector matches with any of the decor's positions, though in the first iteration this shouldn't run anything as there is nothing to match. If the boolean is true, then it must have overlapped with an object, so we look for another position. Else, we set the block's position to that vector. For the rotation, let's have a random value between 0 to 4, floor it and multiply by 90, allowing us to rotate them in 90-degree angles. Finally, let's store the position to a list and increase the length. And if we press play, you can see that our once blank level has been sprinkled with splotches of decor. We have finally reached the conclusion of this tutorial, though in the timeline of making this game, you are only getting started. You have the script for the game, but now you have to focus on designing the puzzles. You can also introduce new themes to add even more variation to your levels. I hope you learned something with this tutorial. As always, there is a GitHub link in the description consisting of code screenshots in case you need to check what went wrong with your work. Thank you for watching, and I'll see you at the next one.